These are the different um, terms in the formula. And now what we have to see is, if we look closely into the this particular formula, we will see that the shear stress is having a linear variation. The shear stress in this torsional shaft is going to have a linear variation. So if we try to draw the shear stress variation, what we can see is that if we are considering a circular shaft, this is a solid circular shaft. If we are considering, the shear stress variation is going to be like this. So this will be the shear stress variation. This will be tau max, and it is going to vary linearly from the center. Okay, it will be zero at the center and maximum at the surface. Similarly, if you are considering a hollow circular shaft, the shear stress variation is going to be something like this. There will be a minimum shear stress at some distance. At the inner radius there is going to be a minimum distance, and at the outer radius we are going to have the maximum shear stress. So tau minimum is going to be at the inner radius and tau maximum is going to be at the outer radius. So this is going to be the variation for a hollow circular shaft. Now we also need to know how do we define this polar moment of inertia. So if you look into the expressions for polar moment of inertia, that is J. So how do we have learned that polar moment of inertia is same as I is said, which is same as Ix plus Iy by perpendicular axis theorem. So if we consider for a solid circular shaft, we know that uh, polar moment of inertia is equal to Ix plus Iy. So Ix is pi d raised to 4 by 64 plus Iy is also pi d raised to 4 by 64. So polar moment of inertia for a solid circular shaft is pi d raised to 4 by 32. Okay. Similarly, if we try to do the same exercise for a hollow circular shaft, so for a hollow circular shaft, we will be having an outer diameter, that is d outer, and you can also have an inner diameter. So the inner diameter will be, let us call it as d inner. So how do we get the polar moment of inertia? All you have to do is polar moment of inertia of uh, the larger cylinder minus the whole polar moment of inertia of the smaller cylinder. So it is going to be pi d outer raised to 4 by 32 minus pi d inner raised to 4 divided by 32. So the polar moment of inertia is going to be pi by 32 into d outer raised to 4 minus d inner raised to 4. So this will be the polar moment of inertia for a hollow circular shaft. Once again, polar moment of inertia is nothing but from the parallel axis theorem, from the perpendicular axis theorem, it will be the sum of Ix and Iy, and Ix and Iy for a solid circular shaft is pi d raised to 4 by 64. So if you do that, we'll get it as pi d raised to 4 by 32, and for a hollow circular shaft we can derive it in this particular manner. So these are the values of the polar moment of inertia for hollow as well as solid circular shaft. We also have to learn one more quantity which is known as the polar section modulus, and we know that from this equation that we have learned, tau max, uh, we have the equation that we have learned is T divided by J is equal to tau max divided by R. So if you rewrite this equation, the torsional moment of inertia, torsional moment of resistance T is equal to tau max multiplied by J divided by R. So this particular term we call it as the torsional section modulus. So if you look closely, this equation is similar to the equation for m is equal to f multiplied by z, where z was considered as I divided by y max. So this equation is similar to that. The torsional section modulus is polar moment of inertia divided by maximum radius. Okay, torsional section modulus is equal to the polar moment of inertia divided by r, where this is the maximum radius. Okay, so if you do this for a solid shaft, so if you do it for a solid circular shaft, j is pi d raised to 4 by 32 divided by the maximum radius is d by 2. We will get it as pi d cube divided by 16. And if you are doing it for a hollow shaft, this will be pi d raised pi by 32 into d outer raised to 4 minus d inner raised to 4, and the maximum radius will be d outer divided by 2. So if we rewrite the equation, we will get it as pi by 16 into d outer raised to 4 minus d inner raised to 4, the whole divided by d outer. So this will be the equation in case of a hollow circular shaft. So basically these equations may come handy while solving the problems. You don't have to by heart, but you have to remember this particular concept. Okay, if you remember this concept, you can easily derive this formula for be it solo, hollow or solid circular shaft. Now, one last concept that we have to understand is that how these shear stresses are acting. Now, what we have to understand is the shear stress is going to act at every cross section. Okay, so if we consider a hollow circular shaft, at every single cross section means if you consider a particular point, cross section is going to be that section that is perpendicular to the longitudinal axis. That will be your cross section. So at every cross section we are going to have shear stress acting on the um, beam. So if we consider an element, if you consider a rectangular element, you will see that shear stress has to act at every particular cross section. Okay, now from the principle of complementary shear stress, if there is a shear stress on one section, section, then there has to be a shear stress on the perpendicular section also. So this complementary shear stress has to act at the perpendicular section also. So which means that the whatever shear stress that is acting on the vertical cross section, the equal amount of shear stress is also acting on the longitudinal section. Okay, so whatever amount of shear stress that is acting on the vertical section is the same amount of shear stress that will be acting at that particular point along the longitudinal section. Okay, so at any point the vertical shear stress and longitudinal shear stress will have the same magnitude. Okay, this is one point we have to keep in mind. Similarly, this is a object that is in pure shear. So this object in pure shear you will learn in another topic of the inclined stresses or the principal stresses. You will see that this object in pure shear is equivalent to a state of diagonal tension and diagonal compression. So this is equivalent to a state of diagonal tension and diagonal compression having the same magnitude as that of the shear stress. Okay, there is going to be diagonal tension and diagonal compression having the same magnitude as that of the shear stress. So when you have a state of pure shear, the state of pure shear will be inducing an effect of diagonal tension and diagonal compression at that particular point in the beam. So this we will try to give more understanding to the idea of diagonal tension and diagonal compression in the coming classes, but for the time being keep this in mind. And before we end this discussions, we also have to discuss one more topic, that is power transmitted through the shaft. Power transmitted through the shaft. As I told you, the shaft is used for transmitting the power from the engine to the wheels. So we have to know what is the power transmitted. We know that the power is equal to force into velocity in linear um, translation. So in circular motion, power will be equal to torque into angular velocity. So most of the time what we will be having is this torque has to be represented in Newton meter, and omega or the angular velocity has to be represented in radian per second. So if this is represented in radian per second, the output that we are going to get will be in watts. Okay, this output will be in watts. So sometimes we will be given the velocity will be given as a frequency f, which is in hertz. In that particular case, what we have to do is omega is equal to 2 pi into f. Okay, omega will be equal to 2 pi into f. If the value is directly given in circular frequency, that is hertz, or hertz is also same as revolution per second. So if the angular velocity is given in frequencies or hertz or in cycles per second, in that case you have to convert it into angular velocity, that is 2 pi f radian per second. Okay, in that case you can then again apply this particular formula, or sometimes it can also be given in rotations per minute or rpm. So n, or the speed n, will be given in rpm, which is nothing but rotation per minute. Okay, rotation per minute. In that particular case again, omega will be equal to, so there are going to be n rotations. N rotation, each rotation is 2 pi radian, so n rotation will be 2 pi n radian, and this is happening in 1 minute. 1 minute is 60 seconds, so this will be 2 pi n by 60 will be the speed in radian per second. Okay, so in this way you can convert rpm or rotation per minute, speed in rotation per minute, to radian per second. Then again you can apply the same formula. Okay, the output that you are going to get will be in watts if your torque is in Newton meter. So this idea of power transmitted through the shaft should also be kept in mind. And finally, to conclude, let us see what are the assumptions that are used in this particular theory. First one is homogeneous material. Homogeneous material is one assumption. Second assumption that we have used while deriving this theory is prismatic circular bars, that is having the same bars having the same cross section. Then another thing that we have used is there is no change in the shape of the bars after twisting. Okay, so after twisting the bars remain circular before and after twisting. Okay, the bars remain circular before and after twisting. And another thing is the cross sections. The cross sections remain straight and circular. The cross sections remain straight and circular after bending, after twisting. Okay, and the another assumption is there is no change in the length or the radius of the shaft. So these are some of the assumptions that we have used throughout this particular derivations. One is homogeneous material, prismatic circular bar, that is the shape is the same throughout. Another one is there is no change in the shape of the bars after twisting, they remain perfectly circular. which means that the cross sections remain straight before and after twisting, and the cross sections remain circular before and after twisting, and also there is no change in length or the radius of the shaft. And also we have to understand the limitations of this theory. The limitations are, this is not applicable for non-circular bars. That is one thing. Second thing is, it is only applicable for small angle of twist. Okay, this is only applicable for small angle of twist. That is, angle of twist will be less than 10 degrees. So these are, and it is also not applicable at regions of stress concentration. Stress concentration means that points where the loads or the couples are applied, or where there is a sudden change in the cross section. So these are the limitations of this particular theory. So in the next session, with this we will stop our discussions on the basic theory that is related to uniform circular bars here, and we will deal with some numericals in the coming session. So before we end, let me just give you a brief recap of what we have learned in this session. First thing is, we understood what is pure torsion. So pure torsion means every single cross section of the uniform circular shaft will be subjected to the same amount of torsion, and that is possible when there is an equal and opposite couple applied on the bar. And in reality that occurs when there is a circular shaft that is fixed at one end and a torque is applied at the free end, and the direction of the torque is represented by double-edged arrows, and the sense is given by the right hand thumb rule. Okay, the thumb has to point in the direction of the arrow, and the torque will be applied on the direction of the in which the fist curls. So that is pure torsion. Then we talked about deriving some of the formulas related to it, and we derived the torsional formula, which is nothing but T divided by J is equal to, where T is the torsional moment of resistance or the torsional capacity, J is the polar moment of inertia, is equal to tau max divided by capital R. Tau max is the maximum shear stress which is at the surface, that is at a radial distance capital R, and which is same as tau divided by small r, that is shear stress at any point at a distance r from the center. This is equal to g theta divided by L, where g is the modulus of rigidity or the shear modulus, theta is the angle of twist in radians, and L is the length of the circular shaft, and this was nothing but the torsional formula. Okay, and we also derived another formula that is related to T is equal to tau max into J divided by R, where which can be written as tau max into ZT, where ZT is the polar section modulus. And lastly, we can also write, we also derived the variation of the shear stress, and we saw that the variation of the shear stress is linear. We drew the variation for a solid shaft, we drew the variation like this, and for a hollow shaft we drew the variation like this. We had minimum here and we had maximum here, so we had 0 here, we had maximum here, so both the variations are linear. So this also we learned, and the last thing we learned was related to the power transmitted, and power is nothing but force into velocity or torque into angular velocity, and angular velocity has to be represented, torque has to be represented in Newton meter, and angular velocity has to be represented in radian per second, and if it is given in hertz, okay, so F will be usually given in hertz, or it may be given in cycles per second, or it will be given in revolutions or rotations per second. In such cases you will have to convert omega is equal to 2 pi f radian per second, and if it is given, the speed is given in rotations per minute, you again have to convert omega is equal to 2 pi n divided by 60. Again you can convert it into radian per second. So this is how you calculate the uh, power that is given by in watts, and if you divide this by 1000 you can get the power in kilowatts also. Okay, so with this we end our discussions on the theoretical part related to torsion of circular shaft. um, we will do some of the numericals in the next lecture. Thank you.